So probably, like many of you, I grew up with the science fiction, and back then, men were walking on the moon. We all expected to have colonies on the moon, to have flying cars, and what have you. The future was great. But that, as you know, it's not really how it turned out. And it's not the rockets, but a different technology that has really dominated the world. So if you had, say, a time traveler from the present day, go back 50 years, only 50 years, and tell them, what's the world really like? You may see something like this. So indeed, we're not walking on the moon anymore, but we have some things that you can argue are actually more interesting. And any technology can be used well or it can be used badly. It's not surprising which one happens to be the first. But let's see a little bit how does that actually translate in a more serious world of science and scholarship. Well, joking aside, I mean, this is really an extraordinary time in which we live. We see phenomenal coevolution of technology and science and society that all influence each other at a pace that's simply unprecedented historically. This is not an exaggeration. What's happening with the internet and computing is like a combination of the invention of printing and industrial revolution combined. But it's more than that because it happens on Moore's law timescales. And that has never happened before. That actually has some challenges associated with it because the humans cannot keep up with the pace of innovation, and that actually can be a real issue. So what do I mean by all this? In science, theory and experiment always depend on each other. They co-evolve. One feeds off each other. Theories simulate experiments, experiments challenge theories, and so on. But science and technology also feed off each other. Technology, in large part, derives from scientific research, but new technologies enable new scientific research. So, for example, the computers themselves, it began by some solid-state physicists inventing transistor in 1950s, and now I use computers to do my research, and you're using one to listen to this. And then science and technology, of course, interact with the society. Society pays our bills, but gets abundant returns, both in terms of understanding of the world and the practical technologies that improve our lives. And I don't need to explain to you why this is happening. But the interesting part is that whereas this was always true since the beginnings of humanity, today it's happening much faster than it has ever happened in the past. So what I mean by cyberspace, the word for my title, Science in Cyberspace, well, it's a metaphorical space. Second Life may be a component of it. But essentially all of our modern society activities, science, scholarship, entertainment, everything, are moving into the world behind the computer screen. And that world is real. It's not some collective hallucination. It actually has real existence, even though it's existence in bits and not in atoms. And if you are familiar with the work of philosopher Karl Popper, I mean, he came up with the thing called World 3, which was the independent world of ideas and concepts that exist independent of us as individuals. But that's pretty much what cyberspace is. So all of things that modern society does are moving into this metaphorical space behind the computer screen. Now, what this is causing and what's resulting from is this amazing synergy between science and technology to which I alluded already. And we've been just going through a period, which is still in the period where sciences are getting used to this. And we talk about e-science or cyber science, and now it's data science. All of these terms are kind of vague, and in particular, data science seems to be especially meaningless because all science is always based on data. But as we become more data-rich and get all these new ways in which we can study the world, we need to develop new scientific methodology. Science evolves, technology evolves, methods have to evolve. And Turns out that all different fields of science are sharing some of the common challenges. First, once you get all these amazing quantities of data, and I'll quantify that in a moment, how do you deal with them? How do you store them? How do you access them? How do you find what data you have? And so on. Then comes the more interesting part, which is how do you discover stuff in the data? Because data are just incidental to that real mission of knowledge discovery. And all sciences are sharing the same challenge. So therefore, there is potentially a great saving of effort and time if we can exchange our knowledge of new methods and new tricks and new ideas. And at the same time, whereas all this computational research is being enabled by information technology and computing, we are also giving new challenges to applied computer scientists and technologists to come up with the better things, faster algorithms, better machinery, and so on. And as the process of that, not just science and technology, but society itself benefits. So people always ask, well, what's big data? And it's a weird term. I would like to say it's more data than you used to have. But here is one definition, which, before I come to that, I should have mentioned this. There's an interesting concept of how do we actually gain knowledge. And late great scientist Jim Gray has come up with these 4 paradigms. The first one is experiment. You all know this. It started with Galileo or even ancient Greeks and carries on till present day. But then came analytical theory from Newton onwards. How do we analytically solve issues and fit equations to the data and so on? And we still do this, of course. In the middle of the 20th century, something new came along, which is computers. And we can call it von Neumann paradigm, where computers are used to solve a lot of partial differential equations, exploding bombs, galaxy formation, whatever. And we still use them for that. So this is computing that becomes a new kind of theory, numerical modeling. And that actually has profound meaning, not just a crutch to the analytical theory. Then in mid-90s, something happened for the observational experimental science. The kind of computing that is data-driven is different from the kind of computing that we use to solve a lot of equations in numerical simulations. The high-performance computing used to be all very numerical. Data-driven computing is not about computing per se. It is really about manipulating information and manipulating the data. And that has different technological challenges. So that's what Jim Gray called the 4th paradigm, the data-driven science or the data science. Well, here I promised you the definition of what big data is. And this one is about as good as any I have ever seen. Is that big data? It's more data than it used to be. Well, everybody talks about it. It's kind of vague. Some of these concepts are deliberately made vague so that we can interpret them in any way we want. Now let me focus on my own science, astronomy, and it turns out astronomy was among the first sciences that actually really bought into this whole concept. And I'm always pleasantly surprised to discover that we're not the dumbest kids on the block. And most of this started in mid-90s with the advent of digital detectors like CCDs and large digital sky surveys, whereby we cover the sky, some wavelength, optical or radio or infrared, sometimes many times, and we count millions or billions of objects. And typically sky surveys now are of the order of hundreds to 1,000 terabytes each. And then the reduced data, actually not reduced, they generate as much higher order data as the raw data, and that grows exponentially. So now petabytes are the currency of the realm. In the circa 2000, terabytes were the currency of the realm. Now it's petabytes, and we're going into exabytes. It's hard to come up with real numbers, but I'm estimating, and I may be grossly underestimating, that today astronomy has of the order of a few tens of petabytes that are stored in some kind of archives. And every day we have several tens of terabytes generated, and both of those grow exponentially. Now, The doubling time for the exponential growth is about 1.5 years, which is pretty much what Moore's law says. And in addition to growth of data volume, the interesting part is the growth of data complexity. And I'll explain that in a moment. Now, just to give a context for the data volume, human genome is less than a gigabyte. Less than gigabyte describes who you are. Right? And human memory, I've seen estimates ranging by many, many orders of magnitude, but roughly speaking, it's of the order of a gigabyte or less, which means that your laptop has more memory than you do. And that's an interesting thing. And I totally believe this, at least in my own case. Now, a book is, well, a couple million books, just the text adds up to a terabyte. And human bandwidth, how fast can you process information, which is what really matters, is of the order of terabyte per year. It is a lot less if you think in terms of text, because nobody can read 2 million books per year, but it's actually a lot more if you're looking at images and videos. On the other hand, you can quibble about informational content of videos, but that's another story. Astronomy is not stopping. Now we're talking about next generation of digital sky surveys and experiments. And in the optical, it is so-called Large Synoptic Survey Telescope that's been approved for construction, has been built in Chile, and it will generate of the order of 30 terabytes per night when it's working. That's approximately the information content of the Library of Congress, if you just look at the printed material, the books. So think of that, generating one Library of Congress per day. And this is also the volume of the Sloan Digital Sky Survey, or in a few days at most, they will generate one of those Sloan Digital Sky Surveys. So it really is a whole new different regime. Radio astronomers are actually even more ambitious. They're building what they call the square kilometer array, and the name does not mean it's a spread over 1 square kilometer. It means that the collecting area of all of the antennas, which are actually spread over thousands of kilometers, is adding up to 1 square kilometer, which is a couple orders of magnitude more than the biggest things we have today. But then they have new instrumentation, digital correlators, and they will generate raw data to the tune of 1 exabyte per second. And exabyte is million terabytes, and terabyte is million books. So you see where that's going. Now, they will reduce a lot of those data on the source very quickly, so that maybe they'll be only generating of the order of a few petabytes per year of high-level data. But nevertheless, it's still a lot of data. So that's astronomy. In every other field, I think biology in particular, is growing much faster than that. In astronomy, we do the sky surveys. This is a tiny little portion of the picture of the galactic center. And every little dot is one or more stars. A couple 100 billion stars in our galaxy, and we have a catalog of the order of 1 or 2 billion of them. Then there are galaxies and quasars and whatever. For each of these numbers, in a given survey, we may measure hundreds of objects, and we find hundreds of millions of them or a billion of them, and so you can multiply the numbers and see where this is going. So this is a lot more than a way in which we did astronomical research in the past, where you would publish a paper, in it there is a table, and in the table there are several tens of numbers, or at most hundreds. So now we do not publish tables. They're all digital databases. You just describe what's in. The interesting part is that the universe looks different in different wavelengths, and each wavelength carries a different kind of information about it. Here is a little mosaic that I chopped out of worldwide telescope display that shows, again, the area of the galactic bulge, how it's seen in visible light, or near infrared, far infrared, which is emission of the dust. You can see anti-correspondence. When there are dark blotches in the near visible light, then there are bright spots in the far infrared, and that's the thermal radiation heat from the dust that's absorbed the starlight. And then there is ionized gas, which is somehow correlated with them, and young stars they're forming. And then there is X-ray sky, which seems like completely unrelated to any of this. So if you observe the sky in any given wavelength, say visible light or radio, it doesn't matter, you're getting a very partial, very biased picture of what's going on. And what we're trying to do these days is we cover the sky in full complement of wavelengths, and now we're moving into cosmic rays and gravitational waves and such. And together, that will hopefully give us a much richer, more complete picture of the universe. So astronomy, over the last 20 years or so, transitioned from enormous data poverty to the embarrassing data richness, or from subsistence economy to overabundance of data. And that is entirely and completely driven by the progress in computing and information technology and very large-scale integration. The same technology that produces integrated circuits, which are famously described by Moore's law, is the technology that produces our detectors and computers that theorists use to generate simulations and so on. And you get this exponential growth with doubling every year and a half. But once you have the data, then you have to discover stuff in them, and you have to unleash all manner of machine learning tools and advanced statistics and so on in order to discover things in them. So real action, what scientists really does, is on that end, on the back end, where the data analysis of the archive happens. And you can think of telescopes and instruments, however glorious they might be, as a front end to the data system, which is where all the real action is. And so that profoundly changes the way astronomy is done. And the same thing, I'm sure, is true in other sciences. So there is a bunch of trends which affect all of different fields, and they're worth looking in some detail. So let's go through them. First, the obvious one is the exponential growth of data volumes. This is why suddenly everybody became aware of the big data and data science and so on, because at some point you can no longer ignore exponentially growing avalanche of data. But the more interesting part is the data have higher quality and higher complexity. We're measuring more things, different things. And astronomy is actually fairly simple in comparison to something like biology or climate, where you measure all kinds of different things. Some are numbers, some are not numbers, some are labels, and so on. And somehow making sense out of that enormous heterogeneity and complexity of large quantities of data is what generates both scientific opportunities and challenges. So all fields have transitioned or are in the process of transitioning from data poverty to data glut. Data were always the basis of science, empirical basis of science, and that's why it was always precious to get more data. But now we have more data than we know how to do it. Now, because we can gather all the data, inevitably we transition from creating data sets, which is what we've been doing all along. You measure a bunch of things, publish, and so on, to data streams that you're constantly getting new data that add to your previous holdings, may revise them, enrich them. And for example, in astronomy, we used to do sky surveys, like one pass on the sky in some filter, set of filters. And now we do it again and again and again, so we transition to the era of panoramic cosmic cinematography. And adding time axis adds a lot more interesting stuff to it. So that means that you can't sit back and think what you're going to do with your data and then do it once. Now you have to actually analyze your data in real time in order to keep up. Otherwise, you'll never catch up. And that's a very challenging thing to do, that there's suddenly dynamical change in the way the data are coming to. The data are changing. We recalibrate them. We add more to them. And so in the past, you would measure a set of things. Say astronomer goes to a telescope, takes a bunch of pictures, measures numbers, publishes a table in a journal, and that's it. And those data stay the way they are forever. And now we don't do this. Now we get these huge data sets, but then we recalibrate them, which means they change a little bit, and we add some more data to them. So in some sense, data sets are alive. They're never finished, and they always change. And that means if you publish analysis for a particular moment in the data stream, then maybe people cannot reproduce what you have done with subsequent data set later. So that means we have to document exactly which data you used and so on. because the data are now coming at us in a constant, exponentially growing stream, we have to then change from traditional way of let's analyze data whenever to having to do it in real time and discover things in real time and react to them. And for example, in astronomy, we discover supernovae, large quantities of supernovae, and they're perishable. You have to follow them up right away if you're going to do any science with them. So it kind of all speeds up the whole process. The other interesting thing, which actually started around turn of the century, is that resources are distributed, not just in terms of labeling, but geography and administration and so on. That, for example, each NASA mission, scientific NASA mission, generates an archive of data from that mission. And those are put online to be available to everybody. The ground-based observatories also are now having archives and collect all the data and store them. The people who get the data can have first crack at them, but then everybody else gets to them. And because there are many different kinds of observatories and institutions and so on, nobody can own all of it. They're inherently distributed and they're connected through the internet. And this gave rise to the virtual scientific organizations. The last line, indeed, is, I think, a very important one, which is that since data used to be the currency of the realm, who has the data gets to do the science. Ownership of the data was the big thing, and some people think still is. They don't realize what's going on. Because when you have very little data, data are precious. When you have lots and lots and lots of data, data are almost worthless. Anybody can have them. It's like money. When government prints a lot of money, that money is not worth very much in the end. And so the one thing that stays as the constant value is not access or amount of data, it's what you're going to do with them, which means do you have expertise, do you have talent, and do you have creativity to discover new stuff? And that's exactly how it should be. That's where the real value should be. So typically, a big data science today, this is made in astronomy in mind, but you can imagine it works for everything else, things like biology or geophysics. It doesn't matter where the data come from, a telescope or gene sequencing machines or set of environmental sensors. You gather lots of data. And then you have to do some good housekeeping. You have to store them and annotate them in a way that can be understood and remembered and can be searched. And you have to find out what data are available where, and then you need to be able to match them together. And we know how to do this. It doesn't mean it's trivial, but we know how to do it. The next step is once you got the data in science-ready form, then the real job begins of having to discover stuff in the data. And this is where there are a lot of challenges, because the methods that we used in the past when we're dealing with megabytes, say, don't scale to terabytes or petabytes. You have to have a new set of tools. And you can do the kinds of science that you couldn't do with small data sets because suddenly you have much stronger statistics. You have so much data you can look for very unusual things. You can look for interesting correlations that you may have missed with less data. And since you're measuring tens, hundreds, even thousands of different numbers for each member of your data set, then we're dealing with a very large number of dimensions. And so these are critical, methodological, practical questions we have to deal with now, and this is where a lot of effort's going on. Finally, once you have all that, then you ostensibly get to understand what's going on, and that's where knowledge comes from. This is a grossly oversimplified picture. There is feedback at every stage of this process that you measure something, you analyze the two things, decide, oh, I should have measured something else, and so on and so forth. And all that is a kind of constantly bubbling, expanding, complex system of scientific workflows, if you want. So remember I mentioned that computers enabled the third paradigm of science, doing theory in a different way through numerical simulation. And at first, people started thinking that, wow, this is just a crutch. Just because it will be too time consuming to solve a lot of these equations by hand, we'll have computers do it. But that's actually missing a very important point. And that is that a lot of interesting science is now inherently non-analytical. It cannot be done analytically. You cannot write the equations and solve them. There is no solution. You have to mimic in the machine what Mother Nature does out there step by step. So algorithm, rather than a formula, is the way in which you approach it. Let me give you a very simple, concrete illustration of this, which I like to point out to my colleagues. That's Newtonian gravity. As you all know, it's a very simple law of gravity. Two masses, distance between them, very easy to compute. If you want to figure out what they'll do, for a given energy and angular momentum, that's Kepler's problem, and any student of physics can do this one on half a page of handwritten notes. That's two mass points, okay? Let's add third one. Solve the three mass problem analytically. Oh, it turns out that there is no analytical solution for that in general, only some very special arrangements. And Poincaré, over 100 years ago, had proven analytically that there is no analytical solution to this problem. And most people didn't understand what that meant. I mean, there's a very fundamental limitation in the way which can learn about the universe, that there is a barrier that analytical theory cannot penetrate a priori. And we do not have the equivalent of analytical theory that will let you do, other than to put in the basic equations in the machine, turn the crank, and see what happens. And that's how all of our knowledge of galaxy formation and star formation and what have you is done today. But the consequence of this is that theory is now expressed as data sets. It's the output of the simulation. And then you have to compare that theoretical data, so to speak, with actual measure, observational, experimental data. And there's a lot of questions there. So there was a fundamental paradigm shift of doing theory in a different way. And the question is there a paradigm shift in the way that we're doing experimental science? But that's an interesting one. So when you look at all this, natural question is, why is this different from what scientists have been doing forever, for centuries? And there are two major differences. The first one is the obvious one, that there is so much data that the rate of data acquisition overrides human capability to process them. And so for the first time ever, we'll never be able to see all of our data. There's just too much of it. So we need technologies that will let us, so to speak, look after the data without human actually have to pay attention in a reliable way. And, we're kind of getting there. The second new interesting thing is what I think is really much more interesting, which is that the complexity of these data, not just their size, but complexity, is getting to be so high that there are certainly important constructs, highly dimensional correlations, what have you, that cannot be comprehended by human brain. It's too complex for us. We ask, how is that possible? Well, look, take a different species on planet Earth, say dogs or dolphins. Well, they're intelligent in some way. You can quibble how much and so on. But your dog cannot understand theory of relativity. It's just beyond the capacity of that type of a mind. Well, I'm sure there is a science that's beyond the capacity of our own minds. And the question is, can we actually nibble at it in some way? And this is perhaps where some synergy of human intelligence and machine intelligence can help us select, find, or downgrade some of those highly complex constructs in a way that we can understand. Altogether, this actually boils down to creating of new scientific methodology. Just like in the past, statistics became part of scientific methodology to deal with kilobytes of data, and then megabytes and so on. Well, now we need new scientific methodology to deal with terabytes and petabytes and exabytes and beyond. And it's not just science, it's everybody else that needs the same thing. So about 15 years ago, there was a grassroots movement of virtual scientific organizations or cyber infrastructure movement. People started realizing what's going on and came up with the concept of frameworks of virtual scientific organizations, where assets like data archives with computers, with analysis, are all distributed, connected on the internet, available to anybody with internet connection. So you cannot have a virtual scientific organization that is just in one place. Right? It can't be at Caltech or Harvard or whatever. It is inherently distributed worldwide. And that baffled some of the bureaucrats in scientific agencies to no end, because it just didn't fit in any of the folders that they had. But that's a whole another story. So that's been going on for a good 15 years now, and now we are on to something different. But one of the first, certainly people say one of the most successful scientific virtual organizations was a virtual observatory, which indeed started about 15 years ago. And the idea was simply this, that you have one-stop shopping to do astronomy with massive and complex data sets, where user gets to their computer, can find the data, can find how to combine them, how to analyze them, how to discover new stuff. We've gone part of the way there, not entirely. We certainly got our data house in order, but in terms of discovery tools, we're still lacking. And this somehow becomes a systemic approach to study of the universe. And the same things you can imagine now in other fields, working with people who are trying to do this kind of thing for climate science, who are trying to do this for genomics, and so on. Astronomy is seen as a model to emulate, which scares me to no end, but it's inevitable people go this way. I would say the most important consequence of all this is it was enormously empowering. And many of you may be familiar with Tom Friedman's book from the turn of the century, The World is Flat, where he pointed out that information technology and internet have flattening playing field. Anybody has a chance to do stuff. And that is profoundly transformative. That now scientists, students anywhere, if they have access to internet, and thanks to the cell phones, they probably have access to internet everywhere, really, can participate, because data are online, tools are online, and literature is online, and your colleagues are online. And so it doesn't matter if you are in Pasadena or Cambridge or any one of those great places. You can be in North Dakota, you can be in Bangalore, you can be in Africa somewhere, and if you have internet connection, you too can play. And so that means that it's not so important where you are, but how clever you are. And I think is going to be extremely, extremely important. We've already seen that happen in terms of economy, but now it's happening in science as well. That doesn't mean that we should stop building experimental facilities like telescopes or accelerators or things like that. We have to have some machinery to generate the data, simply empowering us to do much more with those data than we used to do before. But you get much more bang for the buck if you are focusing on information technology than you have to buy one-of-the-kind hardware that gets expensive because it's not mass-produced. And, for example, 30-meter telescopes are not mass-produced, or Large Hadron Colliders are not mass-produced. What's going on today is the rise of so-called X-informatics, science informatics, where it could be astroinformatics, bioinformatics, geoinformatics, and those are bridge fields that span some domain of science, say astronomy or biology or what have you, with applied computer science and information and computing technology. They're ways to include much broader community than a handful of experts, because previous set of virtual scientific organizations, such as Virtual Observatory, may have engaged hundreds of people as really experts, or thousands, maybe not hundreds really. But you really want a whole community, not just as consumers of these new tools and data, but as contributors as well. And more importantly, because there are all these problems that are common to all different sciences, these are ways in which we can actually learn from each other and share the solutions and ideas and tools and hopefully make a much faster progress because of that. There's one universal problem that I find to be especially interesting, and we've been working on it, and this is also where Second Life comes in, and which is visualization. When the data are simple, visualization is simple. It's the graph on the paper. But when the data are complex, well, then you're out of luck. And philosophers through the ages have been noticing how you don't really understand things intuitively unless you visualize them in your mind somehow. And that applies to abstract concepts like mathematical concepts as well. And so when you can see things in 3 dimensions, well, okay, you can do that. But now you have data sets that are 1,000-dimensional. Now what? And there is important knowledge hidden in there. So this, I think, is one of the key, if not the key challenge for the big data science today. It's not getting the data. It's not doing statistics on the data, finding correlations. It's visualizing stuff. Because that also has to be part of the data mining process. Because you have to see what's going on in order to decide which kind of tools to use. And you have to see the result in order to understand it. And this is where we have a problem, because we're optimized for 3-dimensional world. But it turns out we can actually encode up to a dozen or so data dimensions in a pseudo 3D diagram. And beyond that, it's over. And actually more than 5 or 6 is getting to give you a headache if you're not used to these things. So we have real challenge on trying to understand data of high complexity and dimensionality as possible. Because otherwise we're just wasting a scientific opportunity. There is stuff in there. Can we somehow bring it down to what we can wrap our minds around? And in fact, if you can thinking about it, this is what science is all about. You have a very messy world out there, a lot of diverse phenomenology, and you want to find a simpler set of rules that describe all of it. Like Newton's law of gravity described apples falling from trees and moon going around the earth with the same formula. That's what laws of nature are supposed to do. Well, so we do with simple stuff, that's all done, right? And now we're into much more complex laws of nature. There is no reason why should a law of nature be able to be written as a simple formula on paper. Sometimes you can do it, sometimes you cannot. I think Einstein said things should be made as simple as possible, but not simpler, because sometimes they're not reducible to simple things. And so this is, I think, where we're going to see a lot of fundamentally interesting developments of the synergy of human intelligence and machine intelligence. So remember the 4th paradigm, data-driven science, and people ask, well, yeah, why is this different? We always had the data, so now what? And there are, I think, 3 things that are really new. First of all is there is so much more information in these modern data sets that you can discover diamonds in the dust. Rare, unusual, anomalous things that you couldn't do otherwise. The other thing is that you can put data together. This is fusion of data, say optical and radio and X-ray astronomy together. And together they can reveal things that none of these data sets can actually reveal by itself. So there is knowledge hidden in individual data sets, but the only way to recognize that knowledge is to combine them. And famous examples in astronomy include things like discovery of quasars, where neither optical nor radio was enough by itself, or gamma ray bursts, the birth of black holes, and so on. The third one is the last thing I mentioned, that there is no reason why the universe should be just as simple enough as for us to understand. It's probably much more complicated than that, and we have to expand this boundary of how complex things can we understand in some way. So these 3 things, data fusion, data mining, machine learning, in my mind, is what forms the data science or the 4th paradigm. If you want to be philosophical, you can start asking all manner of questions. I'll trademark this term of epistemology. And I can ask, how is this different from everything we've done in the past? We already know there is a complexity threshold for analytical theory. There's just no analytical theory past some threshold, which can usually be defined very well. And so you need to do numerical simulations. Maybe there is another post-analytical analytical theory, but we don't have it yet. And is there such a thing also for experiment? Is there a threshold in complexity of data, not theory, data, that requires you to have a completely different approach in order to do something with it? I don't know. One other question is that, what does it mean to understand something if you don't have an analytical theory? If you write down again Newton's formula for gravity, one mass, the other mass, inversely proportional to square of distance, you can understand intuitively why this makes sense. But you start with a couple 100 billion mass points and let it rip, and in the end you have galaxies and large-scale structures. And the only physics you put in is that same formula for Newton's gravity, but the phenomenology that came out of it is something you couldn't possibly imagine by staring at that formula. How did you understand structure formation on that basis? You just know that you can reproduce it following a certain set of rules, but did you actually understand anything? That's something we can argue about. So a few more general thoughts about e-science or cyber science or data science. This is not computer science. We use applications of computer science to do our work in other fields. And the data science is not about data. It's all about knowledge. Data are just a step on that way. And the data are cheap. Expertise is expensive. Whether that expertise is in terms of writing software or discovering stuff, expertise is people, and people are expensive. People don't get cheaper according to the Moore's law like your computers do. Another thing is that computer science, or computation, I would say, is a new universal language of science. Just like mathematics is a universal language of science, and it will stay to be that way, it connects different fields. It lets us speak the same language. We can translate domain-dependent things into algorithmic expressions. This is what you do with the data. And that's important because a lot of interesting and important things are highly multidisciplinary. Whether it's energy, whether it's sustainability, it's climate change, or biology, none of these things are just physics or just chemistry or just biology or something. They inherently have to sample in all these different fields of science, which are more or less historically artifact how we organized our science. And the way to talk, in addition to math, is through computation. And if there is no analytical solutions, then computation is the only way we have. So this is important in order to solve some really interesting, complex questions that we have today. So what are we doing at Caltech? We have a brand new research center called Center for Data-Driven Discovery. And we're doing this together with our friends at Jet Propulsion Laboratory. They already have Center for Data Science and Technology. And the goal is to do just what I described, to first provide the tools and expertise to researchers in all different fields to solve their data-intensive problems, but also to serve as this melting pot and catalyzer where we can exchange the ideas. We can recognize a solution we already developed somewhere to be applied somewhere else. And for example, some of the problems we're starting to look at now is how to use some of the tools and methods we developed in astronomy, in virtual observatory, to help people in cancer, medical informatics, or genome biology, and so on. And so that will be very cool. If something that we develop to understand how variable stars change, that we can also now help biomedical researchers make a small step forward in understanding cancer, for example. That'll be a lot more important than any SkyServer result. So we're just starting, and maybe in a year or two, I can speak again and tell you a little more as to what we have actually done. Now, it's not just doing research. It's what you do once you do research, which is how do you do scientific publications, and how do you actually preserve and propagate the knowledge. And that too has changed enormously. First of all, the stuff that we publish is now very much more diverse than what used to be. It used to be just text, equations, and pictures, right? But now we have stuff that can never be published on paper. And somebody has a microphone open, so please close it, because I hear bubbling brook in the background. We do not publish archives that contain terabytes and terabytes of information because they'll require millions of volumes. And why would you do this? Because we never see them that way. Again, somebody has a microphone open, and we hear your camera shutter as well as your... oh, good, thank you. And so the publishing has changed. Data change, so published version has to change. Kinds of things changed, and we go from print-oriented to web-oriented, although we still mimic on the screen what we do on printed paper, but slowly but surely that's changing. And that has all manner of other issues. How do you actually resist that? Because paper, if it's good quality and kept in the right place, can last centuries. And I will challenge you to read your floppy disks from 30 years ago. In addition to political issues, like who has the access, whose job is to do, and so on. And again, our friend with the bubbling brook in the background has the microphone open again. And somebody else, please find out who that is and either eject them or make them stop. Thank you. Now, there is one other aspect that I think is worth talking about, and which is education. Our job as academics is not only to create knowledge, but also to spread it, to teach the next generations how to use it. Now, this opens many interesting possibilities because things are infinitely scalable on the net. This is where all the MOOCs come in and so on. But they can be also customized to an individual. The way we have fixed curricula and fixed requirements for degrees and fixed class sizes in traditional education are simply expression of non-scalability, that you cannot have a class with 100,000 students in it. Well, guess what? On the internet, you can. And so there is a profound change happening in the way we educate people, and I think there's going to be a lot more exciting stuff right there. And the one way which I like to annoy my colleagues is to ask this question. Like, are we doing what society is paying us to do? You know, we're supposed to create knowledge. We're also supposed to propagate it further and teach people how to do. But we're doing a really poor job on this. I think the fundamental reason for this, it's not technological. Technology is way ahead of where academia is this discrepancy of timescales. Technology changes on timescale of Moore's law. And education takes 20 years. And careers are 50 years, and most people stop learning when they get their PhD. And universities change on scales of centuries. And so very quickly, you have so many cycles of discrepancy that it's very hard to catch up. Some people don't even know there is a problem. And so I always quote this sentence from Max Planck, that science progresses through funerals. Well, that's true, but it's a little too slow. And hopefully we can accelerate this by making things so obviously better and doing it online that, like everything else that the internet has touched, the new industry just completely erases the old one. But this is actually a manifestation of a broader trend that through the centuries, technology changes the way we convey the information, which is always in the direction of being more immediate. You don't have to wait for a letter to go 6 months from one end of Europe to another, or for Pony Express to carry it across the country. And also it has a higher fidelity. First from written text to printed text, which is much richer, to radio and telephone, to visual things like television. Now everything is on the internet, and all other media and means of communicating have moved to the internet, and we're now moving towards the three-dimensional web, of which Second Life was one of the early precursors. And it's a fair question to ask, what comes after the World Wide Web and the internet, because that's not the end of progress, right? Back in, say, 1930s and 40s, nobody could imagine something like internet. But here we have it today. What are we going to be using 50 years from now? Well, I don't know. That would be a very interesting thing to do. So this is important not just for education, but also the way we do science, because the way science is done is on the interfaces of human minds and other human minds exchanging ideas, and human minds and information, which is reproduced as text, as pictures, as what have you. And so these communication and display technologies are directly helping science by facilitating these interactions of minds and information. This is what we did back with MICA, the Meta Institute of Computational Astrophysics, as an experiment. And I think it was a part of this natural progression. And even the era of computers, we went from one-dimensional text to two-dimensional flat displays, and now going to three-dimensional displays of information and three-dimensional spaces for interaction. I think Second Life was probably on a bleeding edge rather than cutting edge, and it was too early, but now 3D is coming big way because of the games and Hollywood and so on. And I think before too long, interacting in virtual spaces like this will be seen as a perfectly normal thing. Right? I'm preaching to the converted here, but it's a good thing to mention. Here are some examples of data visualization from Second Life. We're now moving our work to use Unity 3D graphical library as the platform, because 15,000 prims just don't cut it. We're talking about visualizing hundreds of millions of data points. And frankly, there are much better graphics tools and libraries now than they used to be 10 years ago. I don't have any pictures to show you, not that it will help, but that's a very active area of work. And having this immersive, collaborative, interactive data visualization, I think, is going to be one of the important new tools for the big data science. Well, to start wrapping up, so like most scientists, I do nothing all day. I sit in front of my computer, and behind that computer screen is my data, its theories, its literature, it's my colleagues. I'm really doing my science in cyberspace. Sometimes I actually go to a telescope, but I don't do anything with telescope itself. Again, I sit behind computer and look at the data that just came off the telescope. And so science has de facto moved into cyberspace. Parts that we're still doing in an old-fashioned way, partly it's because of the inertia, partly because the technology hasn't gotten to be quite that good yet, but it will. And it's interesting to study this process by itself, asking first, how can we do better science? And second, what can we learn from doing science in this way to apply somewhere else? Let me wrap up then with a speculation that I see. And that is why I call it, there's a coevolution of humanity and technology. And there's this famous scene from 2001, Space Odyssey, that hominid throws the bone with a stick in the air and flips and turns into a spinning spaceship. Well, sticks and bones are some of our first technology, and they gave us opposable thumbs. So we made technology, but technology changes us. But now we're dealing with technology that doesn't change our thumbs, it changes our minds. This is what really counts. I think we have de facto, as a species, already outsourced most of our memory to Google. And there is machine intelligence behind a simple Google interface that figures out what is it that you want once you type a few keywords. And things are only going to get better like that. So like it or not, we are actually co-evolving with our technology. We're co-evolving at the highest level with our minds, not bodies. And we're doing it at an unprecedented pace. Moore's law changes the the pace of the whole thing. So I think we're moving from information technology, just here is your information, to cognition technology, something that helps you understand what's going on. And here, key takeaway points, that all of our activities, including science, scholarship, education, is moving to cyberspace. And all of the sciences are now facing the same challenges and same opportunities, and thus we have to evolve scientific method. And that's important for other aspects of society, knowledge economy, so on, so on. These are the fastest developing technologies in the history of humanity. And therefore, you gain most by leveraging them as opposed to any hardware development. And so that's particularly interesting for countries or institutions where historically they didn't have expensive resources, like big telescopes, for example. And I think it's a part of a much more profound process of the coevolution of humans and their science and their technology. And so I'll end just with this quote from the late great friend and scientist Jim Gray, who noted this very early on, and I'll take your questions at this point. While you're typing them, I'll scroll back and see what are the other questions that have been asked already. TR Amat asked, are we going to have to rely on mental prosthesis, exocortex, to manage future change? Yes, that's pretty much what I just kind of said. And Vic had a comment, I thought human brain had terahertz speeds and petabyte memory. Well, depends what you mean by that. Yeah, there is a lot of cracking between neurons happening, but human minds move on seconds scale, not on nanosecond scale. And how much of the data is stored persistently offline? I've seen graphs for that. Yeah, there are many exabytes by now. Of course, National Security Agency has yottabytes, but that's another story. Vic has a question. Analyze data in real time. Filter for your current efforts. Search for patterns that answer research questions. Yes, that's part of it. A lot of things we have really data filters, just as you say, to look for particular things. Say we're looking for supernova. But that means that you're biasing against everything else. And there may be things that you don't expect that don't match your field. This is something that I think particle physicists worry a lot about, because a lot of data analysis in a place like CERN has always a model involved, and they big simulations see how data deviate from the model. But it's a real issue. If you are too restrictive in the way you analyze the data, you may miss some important stuff. Another question from Vic. What about using parallel processing of unused client computers, processing time like SETI? Yeah, peer-to-peer computing is definitely a solution for some things. But nowadays, those tend to be really public outreach projects more than anything else. And the reason for this is that most of the computational expense is in moving data. It's moving data within computer, from one computer to another, and so on. And so it's just vastly more efficient to run them on your own optimized cluster, or maybe in the cloud. Someday we might actually have the next generation peer-to-peer computing, thanks again to the cloud technology, but we're not quite there yet, I don't think. Now let's see. TR has another question. We need to use multiple dimensions for visualization and rotate them into SL3 space, use various pattern searching filters. Yeah, it's not that simple. You have to figure out which projections of the multidimensional space are actually useful. And which ones are you going to project to XYZ coordinate, or the colors or transparencies or the data shapes or data sizes? And we're experimenting with all that. Part of this is discovering a set of best practices of how do you actually do most effective scientific visualization. So very much a research question, actually. And here again, do computer-using scientists need to have their computers help ensure their computer use doesn't impact their health too much? Well, yeah, there is carpal tunnel syndrome. Some people also get headaches from staring at computer or bad screens too much. And yeah, we sit at the desk way too much, but that's, I think, no different from similar questions that touch any other white-collar occupation. In terms of frying our brains, I don't know, maybe. I would question sanity of some of my colleagues, but I think they came that way. So, Bao has question. In ecological sciences, a great many people use the mathematical models, equations, and tools developed by relatively very, very few people. These models and tools were widely used, but it's difficult for many researchers to assess how good those tools are, let alone create better ones. Is this the case in astronomy? Are there drawbacks to plug in the data, crank out results, use of shared identical tools? Many people involved in creating the tools. Yeah, there is a lot to do with this. By and large, most tools are open. You can dig in as much as you want, and their working is reasonably well documented and understood. It doesn't mean there are no bugs. People discover bugs that nobody noticed for years and years, and then some results are questioned. So that's kind of inevitable, but people approach it in an honest way. I think there's a lot of concern now about reproducibility of scientific research, and it tends to affect mostly fields like biology, where there could be a lot of factors that were not properly taken into account or documented that affect the outcome of your experiments. Or maybe your data have changed, or you didn't write exactly what was the workflow, how you got from raw data to the final result. And there's some of those things can be controlled by better practices. Others, I think, will be inherently difficult to do. So observations of ecological systems, things like that. How many people are making the tools? Well, relatively small fraction of those that are using them, but hopefully as we make more of computational literacy among scientists, more and more will contribute. I think the problem is not having people make you tools, the problem is having people document them properly, and that was always the difficult thing. Vic's question or comment. My observation is that information technology has developed, but humans have not. Do you see any changes in human evolution and brain from advanced infotech? Well, there are books about this. And maybe one simple thing is that maybe we don't remember as much as we used to because we can always look it up. There are interesting questions about digital natives. Do they learn in a different way? Are they better at multitasking, and do they have shorter attention spans because that's what's facilitated by technology? I've seen different opinions on this. I think in the long run, it's inevitable that there will be some kind of changes, and hopefully for the better. Janie's question is, if technology has moved on to surpass our understanding, who and how did they find this technology and recognize its potential? I think you can recognize that there is stuff that you don't know and reasons why you don't know it, like you don't have the right tools to reach it, but it could be out there. And technology may or may not have surpassed our understanding. I don't think it has, because we understand how it works. The question is learning how to design it and deploy it in a way that will actually help us penetrate a little deeper into that world of complexity out there that will let us see things by some clever transformation or whatever that otherwise we couldn't. And at some point, indeed, human minds just won't be able to go past a certain point. But maybe then, again, some synergy of machine intelligence and human intelligence will proceed further. Jess had a question. Oh, hold on. To this one. Scott has leading question. Once computers achieve human-level general intelligence, will they still, I suppose you mean, need human scientists? You finally saw through me, because my ambition is to have my computers do my research and write my papers so that I can just enjoy myself on the beach. Well, seriously, I think we're just building up an interesting partnership with machine intelligence. I don't necessarily think that Skynet is going to kill us all, but it might. We'll find out. Vic has a question. How about using IBM Watson-like computers to help with big data solutions for a massive amounts of data? Well, guess why did IBM develop that thing? I think the whole Jeopardy thing is just a clever piece of advertising. But this is exactly why they have been developing this technology. And I know they've been using some interesting things already. Another question. George, when do you estimate mature classification of filtering tools and user interfaces operating systems? I get me to the data I need instead of spending my time wading through information and data to find the bit I need. Well, we already have something like that. For example, once you have proper metadata, data about data, and they're organized in a proper data system, you can do this. And for Virtual Observatory, we had data registries where you can type in name of your favorite object, and it will tell you all data sets that are available about it and how to get them. So we're getting in that direction. In some sense, Google is doing that by trying to figure out, on the basis of your past searches or patterns, what is it that you need out of 10 million links, which 20 should be on the top. So absolutely we need that, and I think it's getting better all the time. Okay. Vic's question, how about using, hold on, I answered it already. TR question, will we need to sue computers for plagiarisms? I don't know about suing them. I don't think that computers will willingly cheat. They always do what you program them to do anyway. And it's entirely possible for things to be independently discovered. Sometimes this is honest, sometimes not so honest, but again, technology can be used well, it can be used poorly. New question. If computers become so powerful, will the AI become real danger if it surpasses human intelligence, enabling it to manipulate us? I doubt it. I'm agnostic on the question of singularity-ish developments. But my guess is that truly superior intelligence wouldn't care about us. Any more than we care about, say, bugs. But I think some sense that the premise comes from the history of Darwinian evolution on planet Earth. Once you get into the more sophisticated stuff, maybe things don't evolve, let's kill everybody else manner. Or maybe they will. We'll find out again. Mixed question. Will a computer win Nobel Prize for discovering something humans could not? I hope so. I think sooner or later, and probably sooner than you think, machines alone will make discoveries, and that will have to be recognized in some fashion or not. I don't think they need money, or gold medals for that matter. But we are moving into some very interesting uncharted waters here. Jesse, we're talking about petabytes per second, and given getting voice to work on SL is unreliable, this may work for Caltex of the world, but how do you reach villages near Kaolack, Senegal, for example? I think the difficulties with voice in Second Life has nothing to do with state-of-the-art in technology, have to do with Linden Lab management, but that's another story. And if people in Senegal can use cell phones, well, it sounds like they can get voice to work. And I think we'll see how the next generations of interfaces work out. But they're powerful commercial drivers for all this. And we're just riding on the back of commercially driven technology. Well, if no more questions, thank you all for coming and being here. You know how to reach me if you have any other questions. And it's been a pleasure.